Okay, so welcome to the second week of class. Hopefully you guys survived your first week and figured out some of your schedules with remote hours, in person, all that mess. Before we get into lecture today, I first just wanted to bring up some of the suggestions that people made with running the lab. I first want to say thanks to you guys for dealing with some of the hiccups and bugs last week. I'm sure we'll find some more as the semester goes along, but hopefully we can optimize that, figure out how this hybrid lab is working and the like. So over here on this slide that I'm sharing, these were some of the suggestions I got on the Google Doc. You can always add more as the semester goes along. And also from talking to Professor Cash and some of the people running the upper level labs. So it was noted last week that, sound travels within room 316. So if you have headphones, please bring them. I've also noted down here that could help for the in-person lab members. I was even moving into a separate room to jump between different breakout rooms just to reduce the noise. So please try to bring headphones if you're an in-person lab partner. And I've noted here at the bottom, if you have difficulty in affording any materials or stuff that could help with the lab, if you want to let me know, or if you want to let one of the department assistants know, like Betty Gaffney, we can see if the department can assist with that. I saw people trying different camera setups, that we have the one camera webcam at the lab stations. I've purchased like flexible arms to help mount those cameras. I saw some people were able to move them easily, other people not as much. So we were trying to get those by tomorrow. I don't think they're going to make it because Amazon can't get into the Rockefeller building. So we're trying to figure that out of where they're dropped off. But I also saw people bring their laptop or phone. So there's two separate cameras. Also to note, and I even found this, that like my battery died faster, so bring your charger with you. I wanted to ask, the upper level labs are using a Slack, or I don't know if you guys would prefer a Slack channel or Discord or something for text-based question or chatting. I don't know if you guys have any preference of trying that out or not. If you want to throw up in the chat, if you think that would be useful or not. Someone noted that TeamViewer, trying to run TeamViewer and Zoom at the same time is kind of slow, so using share screen. TeamViewer can be allow control that Zoom share screen can't. So that's something to try out and might be worthwhile if you can have a second camera, maybe shut down Zoom on the lab computer when you need to use TeamViewer. And someone else pointed out maybe assigning lab partner roles of, if you have multiple remote lab partners, of one person taking charge of putting the answers in the worksheet or the data in the worksheet, someone focusing more on the manuals. Okay. And I'm seeing in the chat, yeah, Slack or Discord. Okay. So I'll set up, let me make note of this. I'll set up a Slack channel if that's what you guys prefer, out of the two comments, so we can have some text-based questions as well. Also last week, I'm open to your feedback as well, that last week I was trying to alternate between rotating and stopping by the lab stations in person, and then stopping by in the breakout rooms. It was a little time consuming, so Jonathan, the TA, will probably start doing some additional rotations through the breakout rooms on Zoom as well. But if you guys have a preference of more interaction, less interaction, please provide that feedback as well. I'm open to that. And some last things I just wanted to point out here, again, just emphasizing communicate with your classmates and your lab partners, since you guys won't be running into each other in the halls, about if you want to schedule additional times to work together on Zoom or stop by the lab individually. The TA noted, and this is always true, but I know you guys have busy schedules, it's always helpful to read the lab beforehand as well, and take a little bit of time to skim over that And also, I just wanted to point out to remember if you're in person, that if you're getting resistors or using the LCZ meter, to wait your turn. If someone's there, maintain 6 feet or more away from that. And also, if someone gets too close and stuff, feel free to like yell at them and just say like, hey, give me some space. Just a reminder on that COVID policy and stuff. So I didn't know if you guys had any other comments after 1 week of lab or any other ideas to help it run more smoothly. Okay. Well, let me share my screen again. And we'll jump into lecture. And again, just a reminder, if you have a question, jump in the chat, just unmute and the like. So focus of this week's lecture is getting into Fourier transforms. Let me change my pen color really quick to start out. And this is a topic of lab number 2. And with how the semester is organized, we're getting this lecture a little bit earlier before lab 2. Tomorrow will be still lab 1. So you're getting a taste of lab 2 a little early, but we'll be talking about Fourier transforms, a way to visualize data and kind of like a different mathematical language or to understand signals is the main thing with Fourier transforms, which you'll see here, abbreviated FT. You'll be using these not just in lab 2, that's the focus of lab 2, but you'll be using them throughout the semester and the like. And we'll also have a lecture next week on this. So just to present to you what we'll be going over today, that the goals are to go over, the main goal is starting to think in this new way about a signal instead of in time, in frequency instead. And it's a different way of thinking about that data. We'll be going over the history, just some interesting background in the history, but the key things are here. Understanding what a Fourier transform means qualitatively, and then getting into the mathematics of Fourier transforms as well. So this includes reviewing some concepts we'll go over, even and odd functions, orthonormality, Euler's function. We'll go from the qualitative description to the mathematical description in an equation, and then how you can use that to produce a signal with Fourier synthesis, this is something that you'll be doing yourself in lab number 2 as well. This isn't in the uploaded notes, so pay attention to this section as an example of how you can build a signal with Fourier transforms. I want to emphasize that we're going over Fourier transforms in 2 lectures only, but there are entire classes on Fourier transforms. I'm sure there's some over in the College of Engineering, and we could spend a lot of time talking about Fourier transforms, but we're just condensing it down into 2 lectures. So be aware there's a lot more than what we'll be discussing in this class. And to emphasize some of the importance of Fourier transforms, you'll see it brought up in other physics classes that you may take here at CASE. So if you're in solid state physics, K-space is a way to describe the dynamics of electrons in solids and in crystals. And it has to do with their momentum in the solid, instead of their location in space. So you see here with this crystal that you see like the traditional Cartesian coordinates where you might have X, Y, Z or different positions, but then they're explaining things in terms of K-space instead. If you get into MRI or medical physics, you take Professor Brown's class on that as an upper level class, you'll see that it's used in image processing. And also I'll mention in biophysics as well, I use some Fourier transforms for image processing. So you could see here, taking signal out of an MRI, again, you see K notation to indicate that you're in frequency space. And then doing a Fourier transform in 2 dimensions instead of 1 dimension, you can reconstruct signal positions in real space instead, those Cartesian coordinates. In engineering, and we'll get into this at the end of the semester a little bit, that control theory and trying to control actions in an optimized way instead of stopping and starting something during time is a way that you can use Fourier transforms to optimize the control of some machine. I'm not spelling that out. And you can think that's like a very important concept if you're on like a machine line, an assembly line that you don't want to shut a whole factory down just to make a change. So Fourier transforms are used in that area as well. So that's just some big picture ideas of where you might see Fourier transforms come up again, why you should get a good understanding in this class, because it'll be built upon in other classes that you might take or in other areas you might do research or get a job in. And to give a little history about Fourier transforms, it's named after Jean-Baptiste Joseph, I can't, Fourier. His picture is over here. And I'm not pronouncing it right, probably because it's in French and I don't have a good pronunciation of French. And he was alive from 1768 to 1830. And he developed this analysis when he was working in thermodynamics and he was studying heat propagation. And he wanted to describe the changes he was seeing with the heat progressing in some solids. I just say that when I first got here at Case a couple years ago, and I was teaching this class, I took a moment to like look around the outside of Rockefeller. So you know that there's all the names at the top of the building. And I was kind of disappointed that Fourier's name wasn't up there. But I'm just gonna say it's on the side that's covered by Strosacker and his name is probably over there. But do you guys have any guess? His name is on another famous building. I guess Rockefeller is not that famous of a building, but his name is on a famous building. Do you guys have any guesses or ideas what famous building his name might be on? Given how it's pronounced Fourier and how he's complaining that I'm saying it wrong, his first name wrong and stuff. Okay. If there's no guesses, it's just an interesting fact that his name is on the Eiffel Tower. And before I came to Case, I was in Paris and saw that and I nerded out, was a nerdy scientist with that. And if after COVID, I know Professor Rosenblatt does some trips about science in Paris and France and the history there. So you could go, if you guys want to do study abroad physics class in French. I think there's even a portion of that class is learning how to talk about science in French, but that's just an interesting aside. With his ideas about Fourier transforms, it took 15 years for them to be accepted and published. And it was published in the Institut de France. And the reason that they weren't published is that it took so long, it took 15 years, is some other famous names you may know from your mathematics classes and physics classes is Laplace and Lagrange were the reviewers. And Lagrange, whose photo is over here, was more senior. And he didn't like this idea of the Fourier this mathematical tool that Fourier was developing. And Fourier was one of his former students, and he didn't really believe it. So he wouldn't accept it, and Fourier literally just had to wait for him to die for his ideas to get published and accepted. So as an assistant professor trying to get things published and stuff, I'm like, hopefully I don't run into an issue where it takes 15 years to get something published. But obviously, since we're talking about it in this class, this whole course is developed with this. It was a very important idea, so it's a good thing that Fourier stayed persistent. So if you want to hear more about the history, I'm just going to say chapter 8 in the digital signal processing guide that's linked on the Canvas page. You can read more about some of this background. So I always like framing or looking into the history of some of these scientific topics. There's always has interesting stories behind it. So just wanted to share that. But let's get into like what the Fourier transform is. Why are we spending a couple lectures in lab devoted to this? And the qualitative description I'm going to present here is what I'd like you to remember, that down the line, if you don't remember anything about Fourier transforms, this is the thing to remember. And it's the definition that we call Fourier's hypothesis. And there's going to be a lot of Fourier defined terms here where Fourier is in front of it. So I'll try to underline them and point out the difference between them. So Fourier's hypothesis is that any periodic function can be represented as a sum of sine and cosine waves and cosine functions. So that's the shortest, briefest definition. If we want to expand more, and that it can be a sum of sine and cosines, which are an integer multiple which are, I guess I can remove the and, which are integer multiples of the repeat frequency of the original period. And the second portion in parentheses, once we mathematically define this, you'll understand what that means more. So that means any signal that we have in terms of this course where we're doing some signal processing is that we can represent any of those signals, any function that we have, just with sines and cosines. So what does this mean? Or what's an analogy that we can make? Well, that gave it away a little bit. Or can this be related to? That's something similar that you may interact with or encounter. And a nice analogy to what Fourier's hypothesis is with a function and sines and cosines would be in terms of colors. So in the display in your phone, or if you have cool LED lights in your room, how can we represent different colors visually? How can we break those down? So do you guys know the description that you might use for breaking down colors with light on a display or on a printer if you print something out? If you've ever had to change ink on a printer? Like using RGB? Yeah. So Riley and Michael both said RGB. So that's with light. You might also see cyan, yellow, magenta, and depending what you're using with black as well. So that's why I kind of have displayed here, where you can see the mixture of the colors when you have RGB lights. It mixes together with white, with magenta, cyan, and yellow, with black as these. So what these representations are for color, like let's say for RGB, this means that you can build something like, you can represent the color orange would be a value of 237 in red out of 255. Green would be 125 and blue would be 49 out of a max of 255. And similarly, you can do that with inks. But what these are called are basis sets. And it means that you can have various magnitudes of a given set of functions. And that can describe a final formula. Where the functions here would be R, G, and B, and the final formula would be the color orange that you would want to produce. And you can produce a large range of things there. So in a similar way that you have red, green, and blue, if you're trying to produce some type of function so if this is the RGB in colors, if we wanted to do with Fourier transforms, or let's say like Fourier's hypothesis, what our basis set would be different combinations of sine and cosine waves, where we could add all those guys up together, and then you can produce some different signal. So here I've shown like different frequencies. So that's where the component, when I'm saying Fourier's hypothesis, were integer multiples of a repeat frequency. And then the magnitude or the amplitude of those, and if you add those all together, of many different sines and cosines. So you would have different amplitudes and integer multiples of a certain frequency. So if we had like for some signal, let's say we have some signal at some time, you can take some type of measurement here. What that means is you can take a bunch of sines and cosine waves. Let's say you can divide each of those out, and your Fourier transform is going to give you some amplitude or the contribution to your starting frequency or your starting signal. So yeah, I'm drawing like this division signal here. I'm not meaning that hardcore mathematically right now, but that's a way. Right now we're talking about this qualitatively. That's a way to think about what a Fourier transform is. So do you guys have any questions right now about the basis sets? So jump in if you do have any. But a point, getting to the next point, is why. Why would we want to work with these different summations of sine and cosines? And the big key component here is Fourier transforms are very useful in data visualization. So I want to give an example from a sound wave. So this will be related to, I mean, last week, a lot of you guys told me that you were musicians. So how would you tell, I guess, the difference between like a bass singer and a soprano, or a violin and a cello? What, in terms of sound, like what makes the difference between those in what we're hearing?
Physically, it's the amplitude, right? Or is it the pitch? Or are those the same?
There's amplitude is one thing. Cindy's also saying frequency. So those are both contributions. So let's say if you have a violin and a cello playing the exact same note. So you'll have, let's say a note is around 440 hertz. The difference between when you're hearing that on a violin or a cello is, yeah, it has to do what those underlying harmonics and overtones that you have. So that's exactly with like the contributions of amplitudes and frequencies that are underlying that frequency note that is being measured. So for an example, we can take, let's say we're trying to measure a note that's close to an A, and let's say we're measuring a 500 hertz sound wave. And we measure that on a microphone. So the microphone is just, I guess I have my microphone here, which is just picking up changes in pressure in the air, measures those pressure changes and turns that into a voltage. So that's what we're measuring here on our microphone. Our y-axis is voltage, and it's a 500 hertz wave. And over time, you can see that 500 hertz as we're putting this in units of milliseconds here. So if we want to describe this 500 hertz sound wave in time, last week, remember that we introduced like the notation for sine waves, where we would have some amplitude, the sine wave, the frequency in time. So we can say that omega here is our angular frequency. We have our frequency here being 500 hertz, which is equal to where omega, our angular frequency, is 2 pi times nu here to get where this is going to be called our ordinary frequency. So we can define it in terms of ordinary frequency, the angular frequency. We can then also describe it with the period being 2 milliseconds. So the period where we have this repeat, you can see it goes above, below, our period's 2 milliseconds. Our amplitude in this term here would be 1 volt. So you can see there's quite a few descriptors of this sound wave in terms of time that we're using, I guess, 2 variables. And if we want to add that, our phase shift is 0, so technically 3 variables here in time. But if we put this in frequency instead, we could plot on the x-axis, we can put our ordinary frequency here, and we can have our amplitude as well on the y-axis, and we can represent this same signal with this plot here. With our voltage 0 to 1, our frequency 500 hertz, and we have a single peak here. And that has all of the same data that is in this sine wave plot in time over here. So out of these 2 different plots, which one do you think is easier to understand or easier to visualize? If you want to throw that in the chat. So Riley's saying the frequency plot, much simpler, just a single, literally a single data point here, versus a lot more information is in the time domain. So that's one of the reasons why you want to work in Fourier space, that you can simplify your signals down if you're working in frequency space. I will note here that you can, some of you guys might say that there's some information missing here that is in the time data, and that's the phase information, that here with that constant added to 0, that you can clearly see that this is a sine wave starting at a phase of 0 since it intercepts here. That's missing in this data here. But if we want to think about what we're recording, if we're recording like a musical note, that 500 hertz, the phase is just when you're starting to listen to it. So that phase shift doesn't include critical information here for this data. So based on the phase shift, you guys will explore this in lab 2, how your Fourier transform changes with a phase shift, but it will reproduce your signal no matter what. Okay. So after that example, let's get more into these I guess, time and frequency. And the Fourier transform is a way to link them. And when you can link two variables or two quantities with a Fourier transform, that's what we're calling conjugate variables. So Fourier transform is a way to link them, that you can map domains of two interconnected quantities. So we can write this, we have our time domain, where we'll write this as lowercase f of t is our function that has units of seconds. And the Fourier transform, which I'll write as this ft with this double arrow head that goes back and forth, that will link to the conjugate variable of frequency, which we'll write as capital F of nu, which has units of hertz. So it's a way that you can represent the same information with different notations. So an example, you can, I guess, a real world non-physics example would be like an address that, okay, we can say, we can name a place like the White House. We can give it an address of like 1600 Pennsylvania Avenue with a zip code in Washington, DC and the like. We can also do 38.9 degrees latitude by -77 degrees longitude. So those are all the same exact location, but they're different representations. So in the same way, when we have a signal, we can represent it in time, or we can represent it in terms of frequency. And you'll see conjugate variables show up in other physics classes as well. So have you guys seen anything? I don't know if you guys have taken modern physics yet or solid state. Have you worked with conjugate variables in any of your other classes, science classes?
Talked a little bit about Fourier transforms in modern physics, but we didn't go too far in depth.
Do you remember what variables that you guys were working with, or what units you were working with then?
I think we were still doing time and frequency. We talked a little bit about like the wave function moving between like a Gaussian wave packet and like the actual wave function in time space, I guess.
Have you guys gotten to Heisenberg at all? So some that you might see in modern physics would be position and momentum with the Heisenberg uncertainty principle. So these are linked by that, which you can also express in terms of energy and time. So these are conjugate variables related with that principle. And then like I mentioned in solid state physics, you can link Cartesian coordinates and then like k-space vectors, that momentum. So those are some places that you might see conjugate variables come up in physics again. So before moving on, I do also want to note that here defining these conjugate variables, that I included the ordinary frequency here on the previous slide that I said that's related to the angular frequency omega over 2 pi. So throughout this lecture, I'm mostly going to be using the angular frequency. So I don't have to write out as many 2 pi's when I'm writing sine and cosines. But when you're referring to other resources like the Student's Guide to Fourier Transform that's linked on the Canvas site, other people will use nu to represent the ordinary frequency and put the 2 pi's everywhere, but most of the notation I'll be using is the angular frequency. So I do want to note that to you guys. Okay. So yeah, that's most of the first portion of this lecture. That let's describe Fourier transforms qualitatively. What's the concept behind, what's the importance behind it? And the big takeaways that you should have is that we're using a basis set of sine and cosines to represent a signal. And this is a more simplified way to do that. So we're working in frequency instead of time. And the Fourier transform, so I'll be using FT to abbreviate Fourier transform quite a bit. That allows us to switch between conjugate variables. Where we give the example of conjugate variables being time and frequency. That's what we're going to be using mostly in this class, but you'll see other conjugate variables elsewhere. And those represent the same information in different forms. And depending on your application, you'll either want to be working in the time domain or the frequency domain. So any questions so far? Okay. So let's move on to the mathematical representation of Fourier transforms. That will be important in lab 2 as well. And this will get us at, we're gonna have to review some math first to make sure we're all on the same page. And also it will explain, getting into the math will explain why we're using sine and cosine terms. Like, because a question you may have is like, why, like we could also use like, why not pick square waves or sawtooth or triangle waves? Why are we using sine and cosines as our basis set instead of some other signal? I forgot the word set there. So I'm going to break this down a little bit as a refresher of some concepts that are important here. One is even and odd functions. Which has to do with the symmetry around the x-axis. So just as a refresher, I'm sure you guys have heard this when you took trade. I don't know. I remember I learned these in 11th grade, but I can't remember what the class is called. It's been a while. Symmetric. So even functions are the symmetric functions, which we can write mathematically out. F of x for a given function, f of x, it's going to be equal to f of negative x. So out of sines and cosines, which of those is an even function? Is a sine? Sorry, go ahead.
Cosine?
Yeah, so Jack says cosines are even. So if I sketch out a cosine here on this axis, you guys will come to realize I'm not the best at drawing functions. So if that's our starting cosine function, let me throw a different color up here. We're going to say our mirror, our symmetry here is going to be the x-axis here. And if we reflect, oh, sorry. That was the wrong thing. Our mirror is going to be here. Ignore that first line. If we reflect the cosine around the x-axis here, our signal will just overlap. So this is an even function. Okay. So then let me switch back to the blue. So we also want to work with odd functions are then anti-symmetric, which means if we have negative f of x, that's going to be equal to f of negative x. So if we have our same mirror, I'll just draw this dashed line around here. We have a sine function then. And we reflect that. Let me switch to red for the reflected signal. It's going to be anti-symmetric. So, like I mentioned, you guys have probably been exposed to even and odd functions in your mathematics classes for a while. So just remember to do a refresher of what the additive, subtractive, division, multiplicative properties are of odd and even functions. For example, like an odd times an even function, or we'll give you an odd function, odd times odd, we'll give you even, etc., because that will become important in the future and in this lab. The second mathematical concept to review is orthonormality. Which these things are usually grouped together, but they're two separate concepts. So orthogonal functions are when you multiply two functions at each point in x. And if you integrate over all x, you're going to get out 0. So that's an orthogonal function. We can write that out mathematically. I'm sure when you guys are going over wave functions, you guys are going over this as well in modern physics. So if we have two functions f of x and g of x, multiply them together, integrate over all of x, you're going to get 0 out here. So with our previous definition and looking at some of these plots over here, if you have an odd function, would an odd function be orthogonal or not? So if we took f of x is equal to an odd, let's say for our sine function here, f of x is equal to sine, g of x is equal to sine, we multiply them together and integrate, would that equal 0 or not? If we took these blue and red lines here and multiplied them and integrated.
Yes.
Yeah, so that would be 0. Odd functions would be orthogonal. And then even functions here, if we took the cosine term here, if we multiplied those together, we would just get all positive values. So that would give you a constant out. So even functions are not orthogonal. The other aspect of orthonormality is normalization. And this is having everything come out to 1. So if you make an integral of a function times itself equal to 1. So mathematically, that would be the integral of f of x times itself, integrated over all space. You want that equal to 1. And that shows up a lot when you're dealing with probabilities, like again, the wave function. The probability of finding a particle with overall space would be 100%. So that's where you'll see normalization come up quite a bit. So oftentimes to normalize a function, you'll see something come up where you take said function, integrate it over the square here to then normalize that, which we'll see an example on the next slide. So let's just make sure everybody's up to speed on even and odd functions. I'm going to sketch a few out. We'll be switching between colors for a given axis here. Let's say this red function is just going to be a straight line, is f of x. And let's do this purple guy. It's just going to be a straight line. Well, imagine that goes through the intercept of 0. I wasn't so bad with drawing. So for this function f of x, is it odd or is it even?
It's even.
Yeah, so even. And g of x? Yeah, so Riley's saying that g of x is odd. So are these two, are these orthogonal for integrating f of x times g of x? Would those be orthogonal or not?
Yeah, I think so.
Yeah. So those are orthogonal. So f of x times g of x. I guess I could have put some units here. Let's say that f of x is equal to 1, just to keep it simple. That would mean that this would just be equal to g of x. That's an odd function. We said on the previous slide, integral of an odd function is 0, so that would be orthogonal. So let's do another example here of, let's change g of x to a parabola. I'll keep this a dashed line. F of x, well, let's keep it at a constant of 1. So f of x is staying an even function. If g of x is x squared, is that an odd or an even function? So I think, yeah, so Riley added in there that it's an even function. So are these guys orthogonal? If we have two even functions? Yeah, so no, these are not orthogonal. And one last one, we'll keep the parabola, and then we'll make f of x a straight line again. So that would be odd. We said this guy is going to be even. So would these two functions, a parabola and a straight line, be orthogonal or not? So Riley's got yes. And other people feel free to chime in. So that's just a quick check. Seems like you guys are on top of your odd, even, orthogonal functions there. So two last mathematical concepts to remind yourself of is Euler's formula. Power of E in math. And that we can relate with Euler's function, we can relate trig functions like sine and cosines. To exponentials. So we can represent E to the I omega t, where omega is our frequency there. It is the same as the sum of cosine omega t plus I sine omega t, where I is an imaginary number. So this is just a powerful way to connect a more simplified representation or analysis to trigonometric functions. And it can be more convenient at times to use exponentials as opposed to trig functions. So depending on your notation, and next week we'll be going over some of the different notations for Fourier transforms. You can use exponentials instead of cosines and sines. And the last concept, which is nicely described in the digital signal processing guide, is sinusoidal fidelity. And this is a benefit of using sinusoidal functions. So if you have an input signal that is sinusoidal, and you put it through some instrument with what we're doing in lab, if you put it through some mathematical transformations, that's basically what some of the instrumentation is doing, then the output is also sinusoidal. And it's going to be sinusoidal at the same frequency as the input. And this is the key thing. Okay, let's see here. Okay. Can't see the video. Okay. So this is the only function.
It looks like a beer bottle. Not important. I'm so sorry.
No, it's okay. It's the only function with this property. So this is the key thing here. And one of the powers of why we're using sines and cosines in Fourier transforms as opposed to square waves or a sawtooth or the like. And what this means is that your signal won't change shape. With a linear time variant system. So this linear time variant system, that's what we can view our instrumentation. So if we modify our instruments, that means that we're not going to be going from square wave to a sawtooth, that you can always keep working in terms of sinusoidal functions here. So with that quick review, or with those quick mathematical review, here's the recap. Here's what you should take away from it. So again, sine and cosines are a basis set. I'm going to read it to you so you make sure that you go through this. And they're what we're building all of our signals, all of our functions from. And the fact that they're odd and even, the fact that they have orthonormal properties, that they're orthogonal from one another, is why they're a nice basis set to use. Just like R, G, and B are far away from each other on the color spectrum, that's what the orthogonal properties of sine and cosines are. So they're quite different from one another, that then you can reconstitute many different signals from that. So that's where the orthonormality and the sine and cosine come from. Euler lets us handle those in exponents. Sometimes it can be much easier to work with exponents, and that sinusoidal signals stay sinusoidal, even if you're having a variation there. So that's why that's another reason why we're using sines and not some other type of signal shape instead. Any questions from that recap of some math?
I was just curious about one thing.
Mm-hmm.
So I know with Euler's formula that involves like real and imaginary numbers. Anyway, are real and imaginary numbers related in a similar way as like transferring from like the time to frequency domain? Are they different domains, or are they just like part of the same domain, I guess?
Yeah, they'll be part of the same domain. And next week we'll get into, I guess, visualizing this representation of like the real and imaginary space. So we'll go over some details there. And also once you get into lab 2, you'll be doing some Fourier transforms and getting some imaginary numbers out and like, what does that mean? So it'll be like an imaginary number in the frequency domain. So we'll get into more details in the future with that. Any other questions? Okay, we can move on then. We're going to get into describing this instead of qualitatively with math definition. So thinking back to define Fourier's hypothesis in words. Now let's describe it in mathematical terms. So we're going to have a given function. This is our signal that we're interested in. Lowercase f of t. So we're in the time domain here. That we can represent it as this equation. Some constant a naught, and then a summation of going from n equals 1 to infinity. It's going to be in a summation of different amplitudes where we're representing those amplitudes with this constant a of n, where the n is the different frequency component here of some cosines, n omega t, plus different amplitudes of represented by b here for our sine terms, where we have m omega t. I can't read my handwriting. This should be an n for the summation. So this is going to be our definition of Fourier's hypothesis mathematically. So this a sub naught here is we just pull that out from the summation. So the summation not going from 0 to infinity, which we can say when n equals 0, what we would end up having is a naught times cosine of 0 plus bn times sine of 0. So since sine of 0 is 0, that would be bn times 0, a naught times 1. So then evaluating this would then be a sub 0 here. So that's how that gets pulled out in the front here. The rest of this summation here, n is representing that integer multiple of frequency. So that's why we have n omega, or this in period representation, this would be the period divided by n sub here. So going back to like our verbal definition of Fourier's hypothesis, if I go back, we said any periodic function, that's what f of t is, can be represented as a sum of sine and cosines, which is a summation over here, and also this constant. And the integer multiples of a repeat frequency of the original period. That's what this constant n is right here. So that's how we're representing it mathematically. But a sub naught, a sub n, b sub n tell you information as well. So what they're telling you is how much of each term and omega to include in your summation. Or what is the contribution of each frequency? That you then sum up together. And This can relate to like the odd and even functions with the cosine and the sines here. So a naught, an, bn, they can equal 0. Based on if the f of t is odd, even, or neither. So we're gonna, to understand what a naught, an, bn, how they'll contribute, we're gonna also go through another Fourier thing. We've talked about Fourier hypothesis. Now we're going to talk at Fourier transforms. Now we're going to talk about Fourier synthesis to give you a better idea of what each of those terms mean. And that's a way to build up a signal, which again is our f of t, by using Fourier's hypothesis. So we're going to go through this by first determining a naught. It's supposed to be a 1 there. And then we're going to determine the other constants as well. So to first determine a naught for a given signal f of t, the first thing we're going to do, a mathematical trick first. We'll take Fourier's hypothesis, we're going to multiply it by dt and integrate over a period. That's in word form. Here we're taking the equation from this slide here. We'll multiply by dt, integrate the left side. That's what it looks like here. And on the right side of that equation, it's going to be looking like this, where we can break out the constant term here, a naught, multiply by dt, integrate. And since I'm not writing this equation out, that's why I'm going to walk through each term to give you guys time. Again, the other expression here, the summation. So this summation here is exactly what we had on the previous slide. Multiply by dt and integrate over a period, where tau is our period. We look at this portion of the integral here, because it's one period and cosine and sine are symmetric. If we integrate that, all of it's going to be 0 over one period based on that symmetry. Both cosine and sine are symmetric over y. So and they're summed together here, they're not being multiplied. So if you integrate over that, they're going to be equal to 0. So then what we're left with is our term over here with the a naught constant. We can then rearrange this expression here, the left side and the right side, to then be, if we evaluate this integral here, we evaluate a naught dt. If we integrate that from 0 to tau, we're left with a naught over tau. If we then evaluate what does a naught equal, it's just going to be the integral of our signal over one period divided by tau. And what this is equivalent to is then, this is our average signal. This is the time. So what we end up with is the time average signal of ft. So that's what a naught is. It's going to be the time average of that signal.
Does the integral on the very right only equal 0 when an and bn are the same?
This guy over here?
Yeah. Or does it not matter?
No, so the a
Oh, wait a minute. I'm sorry. Never mind. Please disregard. Yep, got it.
Yeah, so the an and bn are just going to be making
Yeah.
higher or lower amplitude there.
Yeah, it's late. Sorry.
No, you're good. And someone might have had the same question. So that's why I'm explaining.
So, what is tau?
So tau is the period of your signal. So if we have a sine wave here, which I can't draw very well. So we're just evaluating, instead of f of t is typically a continuous signal. We're not going to evaluate it from infinity to negative infinity because it's periodic. So we can simplify this down to just be one period here. So this is tau here. Any other questions? Okay. So the next step in Fourier synthesis is more complicated. It's probably going to take 2 slides here. And hopefully my handwriting is good enough for you guys to follow. That's why I uploaded the notes that I wrote more slowly. The second step is then to determine the AN terms. And we're going to be using some tricks that are important based on trig symmetry. So I'd like you to recall, based on different integer multiples, if you go to like your trig functions, over one period, if you have cosine n omega t times another cosine m omega t, where this is the important thing, is that these constants are different. If we integrate that over one period, this integral here, it'll be equal to 1 only when those integer multiples are the same, when m equals n, and it's equal to 0 if those integers are different, when m does not equal n. We can also do that with cosine and sine. And if you recall, when we were discussing odd and even functions, this will always equal 0, regardless of what those integers are. Because we have an odd times an even function, that's always going to equal an odd function. And if we integrate an odd function, that's always going to equal 0. So keeping these trig symmetry tricks and odd even function tricks in mind, and integers, what we're going to do is we're going to take Fourier's hypothesis, the equation that we showed a couple slides ago. We're going to multiply that by cosine m omega t, and we're going to integrate over a period. So to do that, we're going to start with the left-hand side, where we have f of t cosine m omega t dt. And that's going to be equal to, we're going to do this on the other side, where we're just focusing on the summation, because we're interested in the AN constants. So we're going to get AN times cosine n omega t plus bn sine n omega t. We're going to multiply that by cosine m omega t dt. So if we multiply that through, the right hand is going to be that integral. So hopefully you can see where this is going based on this trig symmetry. So all of the terms here, based on these two tricks, is that everything is going to be equal to 0 except when n equals m. So what that will give us is then that integral a sub n cosine squared of n omega t dt. We can then pull out the constant, leaving us with this integral of cosine squared n omega t dt. And if we think of the shape of cosine squared, that's all going to be on the positive side here. Like this. And one period would fall over here if this is 0. That's what that period is. So if we integrate over this shape over here, half of it is going to be filled, the other half is not going to be filled. So that integral we can then say is tau over 2 over here. So what all of this simplifies down to is a of n tau over 2. So that's the right hand of this equation. If we then relate that to the left hand term of that equation over here, what we're going to get and rearrange is a sub n is 2 over tau times the integral 0 to tau f of t times cosine n omega t dt. Is what we get. We can then repeat all of this as well to do bn, and that's going to be 2 over tau, 0 to tau, f of t sine and omega t dt. So this is how you find the constants a and n and b and n, the contribution, the amplitude of different frequency terms when you're building up a signal or Fourier synthesis. And the way of getting these constants and using these trig properties is called Fourier's trick. Another Fourier definition here. And Fourier's trick is defined as like the product of two sinusoidal functions. Is 0 unless they have the same frequency. Here. So this is how you would find a sub n and b sub n terms. And based on the fact that a sub n and b sub n are cosine and sine terms, you can decide or you can figure out if you have a sub n terms, b sub n terms, or both, or just a sub n, just b sub n, or both in your function. So if you have an even function, you can immediately say, since over here, b sub n has sinusoidal, which is an odd function, you can immediately say that all your b sub n terms are 0. If you have an odd function, so this is, when I'm saying function here, I mean f of t, the signal that you're trying to synthesize. If you have an odd function, you can immediately say that all of your a sub n terms are 0, since cosine is even. If your signal is neither even or odd, then that means you'll have both a sub n terms and b sub n terms here. So any questions so far with Fourier synthesis with these derivations of getting what A sub n, B sub n, and A naught are. Okay.
So for n, are we just, that's just what we sum over, right? Will it always be to infinity? And is it always going to be like, I don't know.
So in the perfect world, yeah, you would go to infinity. That's not realistic though. So as you add higher and higher frequency components, usually those contributions decrease more and more. So you'll see in the lab, we'll work up to like, oh, go up to a value of n, I think of 12 or something. So we won't be asking you to go up to infinity. And Fourier synthesis, I would say, is not done frequently, but it's a good way to wrap your head around like what Fourier transforms are. So that's why we're going through it now, and we'll go through it in the lab. But when you're actually doing Fourier transforms, you don't see it as much.
Okay, here's a better question. When you add like cosine m omega t, do you choose one value for m and let everything else cancel out? Or do you just change m into n?
Yeah, so just knowing, I guess that's the Fourier trick here, where you don't have to know a value for n or m. You just know the only way that you'll have any terms left here is when they're equal to one another. So you don't have to know what those constants are.
Okay.
Any questions? Okay.
Thank you.
So last part of the lecture today, we're going to go over an example of doing the Fourier synthesis. And like I mentioned, you'll be doing this in lab 2. You guys will obviously have access to this on the YouTube upload, but this isn't included in the notes because you guys should be working on recalling this during the lab and stuff. So we're going to try to synthesize this square wave, where some properties of our square wave is it's centered around 0. We're going to say the amplitude here is some constant A. I'm going to say this is our signal. This is our time on the x-axis. The period here, we're just going to define as tau as well. And the pulse width that we have is going to be tau over 2, which means the space between each pulse is also half a period as well. So this is a signal that we want to try to build up. So given this signal, some things that we can do to then synthesize it is the first thing we can think about is, will it have AN or BN terms or both? So thinking about the symmetry, which terms will it have in the summation?
I think Bn will be equal to 0 because it's an even function.
Yeah, so we'll just be using AN terms here. If we shifted this signal though, so instead of the pulse being centered at 0, let's say that the start of the pulse started at 0, then what terms would we be using? If instead this pulse started here and went to tau over 2. Would we be using AN, BN, or both? So if I start drawing it out, if our pulses started like this instead.
Riley said Bn.
Okay. Sorry, Riley, I missed that. Yeah, so those would be BN terms based on that symmetry. It would only have signs. And if it was at an arbitrary point where it wasn't symmetric at all, then we would be using a mixture of AN and BN terms. So for the synthesis, if we want to, the first step would be to calculate what A naught is. So if you guys recall, when we derive that, it's going to be the time average of the signal. And we don't even have to do a calculation here. We can just look at our signal here, and we can see that the time average of these pulses would be the amplitude divided by 2. It's on half the time, it's off half the time. So our average over one period would be the amplitude divided by 2. Second step is then to calculate our AN and BN terms. The easiest thing first is to say all BN terms are 0, which you guys defined already based on that since this is an even function, we don't have to even worry about calculating those. So then the next step, I'm going to start it over here, is let's calculate the AN terms. And we're going to start with Fourier's trick, which was that equation that we just derived back over here. So we're going to plug in for A of n, we have 2 over tau. We're going to integrate over one period. We have our function f of t cosine n omega t dt. So that's this equation that we just had on the previous slide. But if we take a look at our signal here, we can apply, we can simplify this down even more. So we can say f of t is symmetric over a period. So that means we can evaluate just over half a period because of that symmetry. So we can evaluate only half a period and then like multiply by 2 and we can get the same answer. So what that will give us is then A sub n is going to be 4 times tau, since we multiply by 2. We're only going to evaluate from 0 to tau over 2. And then we have f of t cosine n omega t dt. So looking at our function, if we go from 0 to 0 to tau over 4, from here, this point to this point, we have an amplitude of A. And then, okay, we're only evaluating from our integral tau over 2. So that's tau over 4. And then tau over 4 to tau over 2 is equal to 0. So we can just ignore tau over 4 to tau over 2 since that's 0. So we can simplify this even more. So we can say A sub n is going to be 4 over tau, integral 0 to tau over 4. From 0 to tau over 4, our function f of t is equal to A. So then we have cosine n omega t dt. So that's just doing some visual inspection of our signal to simplify this down. So going from this integral here, we're then going to evaluate it. So given the lack of space on my PowerPoint, I'm just going to write that guy out again. So if we evaluate the integral, we're going to say A sub n is equal to 4 over tau, A 1 over n omega sine n omega t. We're evaluating that from 0 to tau over 4. We can then plug in for our angular frequency, knowing that our angular frequency is 2 pi times the ordinary frequency. That's also equal to 2 pi over tau. So we can replace all of our omegas in here with 2 pi over tau. So if we write that out, it'll be 4 tau A times 1 over n times 2 pi over tau sine 2 pi n over tau times tau over 4 over here. So plugging in this for omega, plugging in tau over 4 for our t value, and then sine of 0 would just be 0 there. So then we can take this expression here and we can simplify it down. A sub n would then be 2a times the amplitude over n pi sine n pi over 2. So this is how we can then get the constants. Let's say here our amplitude, let's plug in a equals 1, and then we can plug in n equals 1, all of our integer values, dot, dot, dot. So then we can calculate each of these values. So a equals 1 would then be 2 over pi, which then we can numerically say 0.6366197, blah, blah, blah. So this is the numeric answers. Because in the lab, I'll note that it asks for either in terms of, you can include some constants, or the numeric answers, pay attention to that. So that's the value for a equals 1. We plug in a equals 2 into this equation. That would be sine of pi. So that's going to give us 0. A sub 3 would then be -1 times 2 over 3 pi, which is equal to -0.2122, dot, dot, dot. So you can repeat this going up to a given integer value as well, but you can, so this is telling us that there's a larger contribution from n equals 1, no contribution from n equals 2, to then build this up. So if this is for when this is symmetric here around 0, but if we change this again, like how I was asking, if we shifted this over, so the pulse started at 0, we could then our a sub n terms would be 0, and our bn, if we evaluated this, it wouldn't be the same expression. That's why I'm bringing this up. We would have -a over n pi times cosine n pi minus 1. So this expression is different, but it will actually give the same magnitude for these numeric values instead. And this has to do with some of the complex notation of using cosines and cosines and sines. And if you applied like Euler's equation and expressing this in exponentials, it would actually be simplified. So we'll get to that next week with the different notations. But this example hopefully will help you guys in lab 2, which you'll start not tomorrow, but the next week. So that's what I had with the Fourier synthesis. Was there any questions with that worked example?
I guess just in general, then what would you do with your values for a sub 0, a sub n, and b sub n? Would you be able to make like a graph in the frequency domain?
Yeah, so here we're working in the time domain here with the t. So in the frequency domain, you would have peaks that would represent each of these. The amplitude of those peaks would be these numeric values here, and where they would be on the frequency domain would then line up. This would be closest to 0 and with those higher frequencies. And we'll see that next week when we get into this. But if you plug in all these values in the time domain, in this summation here, what you would get is then, let's say, if you went out to infinity, you would add all those summations together and you would get this red signal here. That's what you would get out. If you're only working up to 3 terms, and you guys will be doing this, you'll start to see it get closer and closer to a square wave. But the fewer and fewer terms you have, the more rounded it is. If you think about like, okay, if you just start with only a = 1, you're gonna have a sine wave there. And as you keep adding more and more frequency components to that sine wave, it'll get closer to a square wave. So you'll be doing that in MATLAB, adding more and more terms to visualize that. Any other questions? Okay. So I also just want to point out here, so next week we'll be talking about, again, the notations, discrete versus continuous data, and an important thing of knowing what the Fourier transforms are for certain signals. So we'll be going over that next week. But I did want to point, there are lots of resources out there for Fourier transforms. This is uploaded on Canvas if you want to get into a lot of detail with Fourier transforms. Application to signal processing is in the DSP guide. And then here's quite a few nice YouTube videos that if you look at the PDF notes, I linked to them. They're also linked here to just wrap your head around, like, as I mentioned, this is like a different language, a different mathematical language of understanding what signals are. So taking a little bit of time to watch these other videos, I think is helpful to understand why we're using sine and cosines, etc. Yeah, 3 blue, 1 brown. It's a really nice one with the visual representation of why sine and cosine, why the periodic functions there. So yeah, if you have any questions in the meantime, let me know. I'd say tomorrow in lab, focus on like the different instrumentation and the like, but after wrapping up lab 1, it might be useful to take a look at this video again for like a refresher. And I'll try to recap a little bit next week as well of what we went over today, so it's fresh in your mind for when you start lab 2. Cool. Okay, so I may have saved some notes from my previous class, so I will check on that if I saved them to the wrong thing or uploaded the wrong thing, and I'll put the correct PDF. Sorry about that. Okay, cool. Any other questions? Okay, well, I'll see you guys tomorrow then for lab.
Thank
Thanks.
you, Professor.